In this example, we're asked to find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1. So we can imagine here the ellipse is going to extend along the x-axis from a to negative a, and along the y-axis from b to negative b. Okay, so we can kind of imagine here the ellipse that we're trying to find the area of. One thing I could do is I can isolate the y in this equation, so I can express the function that gives me the top half of this ellipse. So doing that, I would have, let's see, y squared over b squared equals 1 minus x squared over a squared. And then I can multiply the b over here. So I get y squared equals b squared minus b squared over a squared x squared. And then square rooting that, I get y equals the square root of b squared minus b squared over a squared x squared. So that gives me the top half of this region. Actually, I can factor out the b there, so I can just put the b on the outside. And then that makes it look a little simpler. 1 minus x squared over a squared inside. And then if I'm finding the area under this curve, I'm going to be using the symmetry in it. If I just take the integral from 0 to a, then I can multiply that by 4 to get the whole ellipse. Okay, so the area enclosed by the entire ellipse will be 4 times the integral from 0 to a of b times the square root of 1 minus x squared over a squared. Now this looks like it's in that form that we had before, where it is in the a squared minus x squared form. In fact, to get it more into that similar form that we had before, I can combine these two terms here. 1 minus x squared over a squared, getting a common denominator there. I think might make this look a little bit nicer. Because then I can also take the square root of a squared in the bottom, and so I get b over a on the outside, and then the square root of x squared minus a squared, or a squared minus x squared. Okay, so actually here I'm going to write that up here, save myself some room. So it's 4 times b over a, integral from 0 to a, of the square root of a squared minus x squared. Okay, so here I'm going to remove this stuff down here so we can use that room there to integrate. Alright, now this looks like it's in the form where we can do the x equals a sine theta substitution. Okay, so we're going to let x equal to a sine theta. So dx will be a cosine theta. So we'll substitute all that stuff in. Let's see what we get now. So we got 4b over a, integral from 0 to a. And actually here I'm going to leave those limits of integration for now because we're changing the variable. Right? We're changing to a new variable. So let's see, I'll have a squared sine squared. And then dx will be a cosine theta d theta. Notice we're changing to the variable theta, so our limits of integration should change to reflect the new variable. So let's think about what those new limits of integration would be. So let's see, our old limits of integration were x equals 0 and x equals a. So when x equals 0, what do we get for theta? Well, here let's put in 0 for x here. And so 0 equals a sine theta, so dividing the a, 0 equals sine theta, which we know that occurs when theta equals to 0. And let's see, when x is equal to the other limit of integration at a, means that a equals a sine theta. So dividing a, we get 1 equals sine theta. And that occurs at the angle pi over 2. Okay, so our new limits of integration will go from 0 to pi over 2. And actually, this is good because now it saves me the last step of having to change back to the original variable x, because now I can just evaluate it at the end in terms of the variable theta. So now let's do a little bit of factoring. I noticed we can take out the a squared from the square root and becomes a on the outside. And then we also have another a here that factors out. So what's left is the square root of 1 minus sine squared, and then cosine theta. Here I can divide out the a there. And then we know that the square root of 1 minus sine squared will be the square root of cosine squared, which will just be cosine without the square root. Okay, so already our integral is starting to look a lot better. We got 4ba on the outside here. And then we got cosine theta times cosine squared theta. Okay. And remembering we're going to integrate from 0 to pi over 2. And we know how to deal with this when we have an even power of cosine. Remember, we're going to use the power reducing identity, 1/2 1 plus cosine 2 theta. So now this one's pretty easy to integrate. So we'll have, when we integrate, theta plus sine 2 theta over 2. And then we'll evaluate from 0 to pi over 2. Now let's see, I've got 4ab times 1/2, so that's 2ab. And then let's see, evaluating it at pi over 2, we'll have pi over 2 plus sine of 2 times pi over 2 would be sine of pi. And then evaluating it at 0 will just be 0. And then we also notice that sine of pi is equal to 0, so this guy is 0. So in the end, we're just left with 2ab times pi over 2, which will be pi ab. So the area inside the whole ellipse will be pi times ab.